Hacks and Vulnerabilities in Automotive, Part 2. The focus of this presentation is SecOC, which is AUTOSAR architecture module. Recap from Part 1 of the series of presentations. How crucial is cybersecurity in automotive? What are the key factors associated with attacks? What are the attack vectors in cars? And what are the threats of attack vectors? And vulnerability assessment of a 2014 Jeep Cherokee. Key points from Part 1 presentation. CAN bus is extremely vulnerable to attacks. Software over-the-air updates are highly critical in terms of security. Key factors associated with attacks are the attack surface, cyber-physical features, and the internal network. Security is not an add-on feature, but a design issue. The risk management should begin at concept phase. I'm going to tackle each key point separately. In this presentation, I'm going to describe one of the methods we can use to prevent attacks on the CAN bus, which is SecOC. In the next presentation, I'll discuss how we can use code signing to limit attacks on software over-the-air updates. CAN bus is extremely vulnerable to attacks, but at the time of introduction, the vehicle's networks were isolated from remote connectivity. So there was no risk of a remote attack, hence no need for cybersecurity. Preventing access to the CAN network is one mean of preventing remote control of a vehicle. Once on the bus, an attacker can imitate a legitimate sender and gain control of the behavior of the entire vehicle. The attacker can read and tamper with sensitive data. In-vehicular communication can be prevented by implementing SecOC in the communication network. SecOC adds security to the outgoing message to achieve integrity and authenticity of the message. Secure onboard communication, SecOC. SecOC module is present in the AUTOSAR architecture and is designed to protect the in-vehicular communication. It is specified to check the authenticity of a single transmitted PDU in order to detect attacks such as replay attack, spoofing, and tampering. SecOC can be integrated into CAN, Ethernet, or FlexRay networks. With SecOC implementation, the attacker has to know the sender's secret key in order to spoof a message. This is AUTOSAR SecOC architecture diagram taken from classic AUTOSAR release 1911. Here, the PDU router receives the PDU from the upper layer to route it to the respective network interface. Before it routes to the network interface, the PDU router passes it to the SecOC module to add authentication to the PDU. The SecOC module does so by using services from the Crypto Services Manager and then passes it back to the PDU router. The PDU router then routes it to the network interface. Similarly, the PDU router receives a PDU from a network interface to be routed to an upper layer. The PDU router first sends it to the SecOC module for authentication. The SecOC module authenticates it again by using services from the Crypto Services Manager and then passes it back to the PDU router to be routed to an upper layer. This is how SecOC functionality works in the transmitting ECU. The SecOC module interacts with the PDU router, the Crypto Services Manager, and counter. The counter here is not an AUTOSAR module, but is implementation specific. The PDU router receives a PDU from upper layer. PDU router passes the PDU to the SecOC module to add authentication. The SecOC module first obtains freshness value from the counter. The SecOC module then generates authenticator using services from Crypto Services Manager. Authenticator is encryption of freshness value and PDU using secret key. SecOC then attaches the freshness value and authenticator to the PDU frame and returns it to the PDU router. PDU router then routes it to the respective network interface. So SecOC functionality in sending ECU is PDU router routes PDU to SecOC module to add security to the PDU. SecOC module takes freshness value from counter, timestamp or counter value. CSM module provides cryptographic services to SecOC module to generate authenticator. SecOC module encrypts PDU and freshness value with secret key to generate authenticator, which is MAC, message authentication code or signature. If the key manager uses symmetric keys, then the authenticator generated is MAC, and if asymmetric keys are used, then the authenticator generated is signature. SecOC module appends freshness value and authenticator to the PDU, creating a secured PDU. Secured PDU is returned to PDU router for transmission. This is how SecOC functionality works in message receiving ECU. The PDU router receives a secured PDU frame from network interface. Secured PDU has authentication added. The secured PDU frame is forwarded to the SecOC module for authentication. The SecOC module strips freshness value and authenticator from the frame. The freshness value is then compared with the current counter value to determine freshness status. If the received frame is not considered fresh, then it is perceived to be a replay attack. New authenticator value is generated with the attached freshness value and PDU for comparison with the received authenticator value. If authentication is successful, then the PDU only is forwarded to the PDU router for routing to the upper layers. This is how SecOC functionality works in the receiving ECU. PDU router sends the received secured PDU frame to the SecOC module to determine authenticity. The SecOC module strips the secured PDU frame into PDU, freshness value, and authenticator. New authenticator is generated by encrypting PDU and freshness value with the stored secret key. The received freshness value is compared with the current freshness value to verify freshness. If the freshness is verified and the generated authenticator matches the attached authenticator, then the PDU is considered to be authentic and passed to the PDU router. Authenticator is data that is used to provide message authentication. In general, the term message authentication code is used for symmetric approaches, while the term signature or digital signature refers to asymmetric approaches. Extract from AUTOSAR 4.3.1. The specification is based on the assumption that mainly symmetric authentication approaches with message authentication codes are used. They achieve the same level of security with much smaller keys than asymmetric approaches and can be implemented compactly and efficiently in software and in hardware. However, the specification provides necessary level of abstraction so that both symmetric approaches as well as asymmetric authentication approaches can be used. Classical CAN has a limitation. Classical CAN frames provide a payload size of only 8 bytes. The PDU along with the freshness value and authenticator cannot be supported in one classical CAN frame. This leaves two options, both of which have an advantage and a disadvantage. The first option is to truncate freshness value and authenticator to shorter lengths. The disadvantage is that it reduces security. The advantage is decent communication is retained. The second option is send authenticator in another frame. This configuration is available in AUTOSAR. The advantage here is that it improves security. The disadvantage is that it has an impact on bus load. Further information about SecOC. Networks CAN-FD, FlexRay, and Ethernet do not have payload limitation. Secondly, key management and freshness value handling are not dealt with by AUTOSAR. Also not dealt with by AUTOSAR is the recovery strategy. For instance, how to deal with failed authentications and how to recover the system operation when participants are out of sync. Finally, SecOC can prevent replay attacks. However, depending on how counter timing is handled, may also be able to prevent relay attacks. This is end of part 2 of hacks and vulnerabilities in automotive presentation. Hope you enjoyed it. Part 3 will concentrate mainly on code signing software. Thank you and bye.